Hello, and welcome to the Chapter 7.1 lecture on Laplace transforms. So, a Laplace transform is a way of converting a differential equation into an algebraic equation, which we can then solve using ordinary algebra, and then undo the Laplace transform on the result to arrive at the solution to the differential equation, or even system of differential equations. It will convert a system of differential equations, for example, into a system of algebraic equations, and we know how to solve a system of algebraic equations. And then we can solve that and convert it back and solve the system of differential equations. As you can already gather from this, it is a profoundly powerful technique and method, but accompanying this, it will require several days of theory before we can really put it into practice. Although at the end of chapter 7.2, just the next one, we'll already see applying it to a simple differential equation to see the idea of how it works. So the Laplace transform is defined as follows. Given a function, f, defined for t greater than or equal to 0, then the Laplace transform of f, denoted with this calligraphic L, is the integral from 0 to infinity of e to the negative st times f of t dt. Provided that that integral converges, which it almost always does, because e to the negative st is negative exponential growth, so we'll override almost any f unless f grows supra-exponentially, like e to the power of t squared, but such functions are very uncommon in practice. So the Laplace transform will virtually always exist. So let's do an example. Let's find the Laplace transform of 1. So I put here in the upper right that definition of the Laplace transform. The Laplace transform of 1 is the integral from 0 to infinity of e to the negative st times f of t, which in this case is 1, dt. Integral of e to the negative st is negative 1 over s times e to the negative st, and we are evaluating that between 0 and infinity. We plug in infinity and subtract the evaluation at 0. Okay, technically, a integral from 0 to infinity, that is the limit as we approach infinity. But as our input approaches infinity with a negative sign by it, then it's like e to the power of negative infinity, which approaches 0. So this is 0 minus negative 1 over s, and e to the power of 0 is 1. So we wind up with 1 over s. In the integral, we thought of s as a constant, but at this point we think of s as a variable, as an input to the resulting function. So the Laplace transform, it accepts a function of t, and it outputs a function of s. Let's do another example. Let's find the Laplace transform of t. Okay, we plug this in, and we have that. And this is a classic integration by parts problem. And let me remind you how integration by parts works. We separate the integrand into a product of two functions. We integrate one of them and differentiate the other. And that will give us our new integrand in the following way. And we are evaluating that between 0 and infinity. The integral of negative 1 over s, e to the negative st, we divide by another negative s. We have a triple negative and a 1 over s squared, e to the negative st. And now evaluating this between 0 and infinity, it looks like this. This part is at infinity. This is because this component, as t approaches infinity, this approaches 0. Yes, t there approaches infinity, so it's of the form infinity times 0. But if you do L'Hopital in this case, you'll see that it approaches 0. And then this is a simple e to the negative infinity. It also approaches 0. And then when we plug in 0, we have a 0 minus 1 over s squared times 1. E to the 0 is 1. So what we wind up with is 1 over s squared. Let's do another. What's the Laplace of e to the at? We can use exponent laws here. Combine that into a single exponentiation. Let's factor out the t. And now the integral is 1 over a minus s times e to the a minus s t, evaluated between 0 and infinity. And remember that the Laplace transform is when it converges. When s is greater than a minus s is less than 0. So what we technically have is a domain restriction to s being greater than a. And the result, we plug in infinity, subtract the evaluation at 0. Because of our domain restriction, that guy is negative. So this is 0 minus 1 over a minus s times 1, which is 1 over s minus a. And in practice, we never need to worry about these domain restrictions. We just say that the Laplace transform is 1 over s minus a. We can also take the Laplace transform with sinusoidal functions. Here's the Laplace transform with sine of 2t. We plug it in. This is an integration by parts problem. You can pause the video if you want to look at the details. This is the one where we need to integrate by parts twice and solve for the integral, and we wind up with the Laplace transform with sine of 2t. And we can compile these various Laplace transforms that we compute into a table. So we found that the Laplace transform of 1 is 1 over s. The Laplace transform of t was 1 over s squared. And one can then find the Laplace transform of t squared, t cubed, etc. And by induction show that the Laplace transform of t to the n is n factorial over s to the n plus 1. Remember that the factorial just means that we compute the product down to 1. So for example, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1, etc. We found the Laplace transform of e to the at. And for sine and cosine, one ends up with those. And hyperbolic sine and hyperbolic cosine, you can ignore those for now. We'll talk about those at the beginning of the next section. Some of your homework problems involve finding the Laplace transform of piecewise defined functions. So like here's a function f defined as 0 for t between 0 and 3, and 2 for t greater than or equal to 3. Here's the graph of the function. It's 0 up to 3, and then it's suddenly 2. What is the Laplace transform of that? We plug it in. And remember that the way to find the integral of a piecewise function is just to break it up into 2 integrals over the 2 corresponding parts. So this is the integral from 0 to 3 of e to the negative st times the function there, which is always 0, plus the integral from 3 to infinity of e to the negative st times the function definition on that domain. So one can then evaluate each of those integrals separately and come up with the Laplace transform. Recall our concept of linearity. We encountered this in the context of linear differential equations, and the linearity axioms were that a function L is linear if it distributes over sums and you can pull out constants. Now, an important property of the Laplace transform is that it is linear. The Laplace transform of a sum is the sum of the Laplace transforms, and we can always pull constants out of the Laplace transform. Both of these properties are because integration is linear. So for example, the Laplace transform of f plus g, we plug that into the definition of the Laplace transform, e to the negative st times f plus g. We can separate that into the integral of a sum, which is the sum of the integrals, and each of these individual integrals is the Laplace transform of the corresponding function. And similarly, we can pull a constant out of an integral, and thus we can pull a constant out of the Laplace transform. So we can use this to evaluate Laplace transforms of composite functions by breaking it up into smaller Laplace transforms. So for example, the Laplace transform of 5t minus 2e to the 3t, we can break that up into a difference of the Laplace transforms. We can pull out constants, and then we can use the Laplace transforms that we already found. The Laplace transform of t is 1 over s squared. So we have 5 times 1 over s squared. And then minus 2 times the Laplace transform of e to the 3t. The Laplace of e to the rt is 1 over s minus r. So this is 1 over s minus 3. So we wind up with this. Go ahead and try your hand at this. So we found that the Laplace transform of 1 is 1 over s, and the Laplace of sine of 2t is 2 over s squared plus 4. Find the Laplace transform of 5 plus 3 sine of 2t. Go ahead and pause the video, or even think about it mentally. You might be able to do this mentally. So we have the Laplace of 5 plus 3 sine of 2t. We can break that up. And now how do we deal with the Laplace transform of 5? Well, we can think of that as 5 times 1. And then we can pull out the 5, and we know the Laplace transform of 1. So the Laplace transform of 5 is 5 times the Laplace transform of 1, which is 5 times 1 over s. And Laplace of sine of 2t is 2 over s squared plus 4, per that. So we wind up with our Laplace transform. All right, that actually is all to this extremely short introduction to Laplace transforms. Next time we'll talk about finding inverse Laplace transforms and then see how we can apply this to differential equations, and we'll see our first solving a differential equation with Laplace transforms. Have a great one.